In this last lecture of the module, we want to introduce predicting when to expect precipitate formation. In the first part of this lecture, we'll look at some situations where we'll want to predict whether or not, when there's several cations and anions present in solution, whether or not any combination of cations and anions might precipitate out as a solid and how you might predict that. In the second part of the lecture, we'll look at some more advanced topics also concerning precipitate formation. Now, when a solution contains several different cations and anions, the probability increases that some combination of cations and anions could form precipitates. We can predict what compounds might precipitate if we remember the following. An ionic salt will start to precipitate, in other words, form a solid, come out of solution and form a solid, whenever its solubility product Q exceeds its KSP value. Now, let's see what we mean by that. Let's consider the equilibrium, solubility equilibrium for cerium hydroxide. We've written this before. If cerium hydroxide went into solution, it would form cerium 3+ ions and hydroxide ions. We know the KSP for this because we can look it up. It's quite small, so this is not a very soluble salt. And we can write out what we've called the solubility product for cerium hydroxide, which would be cerium 3+, the concentration of cerium 3+, times the concentration of hydroxide in solution, cubed because of the 3 in front of the hydroxide. Now, this expression, this solubility product expression, will come out equal to the KSP, as we've written here, when the system is at equilibrium. Well, what about when the system is not at equilibrium? And what I mean by that, for example, is when there's too little or too much cerium 3+ or hydroxide in solution. Well, what we can do is we can calculate a Q value, which in the past we called a reaction quotient, using the same solubility product expression, but with the current non-equilibrium concentrations of cerium 3+ and hydroxide. Now, when calculating Q, you need to remember that we need to consider all sources of cerium 3+ and hydroxide in solution. This may be a little more plain when we do some examples in the future. So, if we calculate a Q value, again using the same expression, and it comes out equal to the KSP value, what we'd say is that the system is at equilibrium, but applied directly to solution concentrations, we'd say the solution is saturated with dissolved aqueous cerium hydroxide. The solution has as much cerium 3+ and hydroxide it can tolerate before forming precipitate. So we say the system is at equilibrium. If Q comes out larger than KSP when you do this calculation, it means that the system, of course, is not at equilibrium, and precipitation of cerium hydroxide solid must occur to reduce the solution concentrations of both dissolved cerium 3+ and hydroxide. Because when Q is greater than KSP, there's something about either the cerium 3+ or the hydroxide concentrations, or both, that makes the solubility product come out to be greater than the KSP. If that happens, you get precipitate, and you'll get precipitation of cerium hydroxide solid until this solubility product is reduced back down to the KSP value, and then cerium hydroxide will stop precipitating. And of course, if Q is less than KSP, then the concentrations of cerium 3 plus and hydroxide in solution taken together are not high enough to cause precipitation of cerium hydroxide solid. Now, the second thing you need to remember is what I noted up here, and that is that the above statements are true even in a solution with many other ions and molecules present. So if there are other things besides cerium hydroxide directly that are contributing to the cerium 3 plus or hydroxide ion concentration, you need to consider them when you're calculating the solubility product. But this statement actually expands on this a little bit and says, look, there may be many other things going on in solution besides cerium hydroxide trying to decide whether or not it's going to precipitate. Keep in mind that all those other situations also have to be satisfied. So the other things in solution, if they're acids, have to behave according to their Ka values. If they're bases, according to their Kb values. Water has to still satisfy the Kw expression. Now, don't let this alarm you. It's just something that you need to keep in mind when you're considering whether or not something's going to precipitate out of solution. So let's look at some example calculations. Here's the first example. A solution is prepared by dissolving the soluble salt cerium nitrate, remember nitrates are really soluble, in water until the concentration of cerium 3 plus is 0.00788 molar. Nitrate here is going to be a spectator. If we adjust the pH of the solution to 8.10, will cerium hydroxide precipitate from the solution? So what we're going to do is intentionally adjust the hydroxide ion concentration by adjusting the pH, and then we're going to ask, well, taken together, is there enough cerium 3 and enough hydroxide from this pH value to precipitate cerium hydroxide from solution? Well, in order to do this, it would be nice to know what the hydroxide ion concentration is, so we'd use our expertise from the acid-base chapters and say that at a pH of 8.1, the hydronium ion concentration would be 7.94 times 10 to the minus 9, which means the hydroxide ion concentration would be 1.26 times 10 to the minus 6. Now we'll calculate the solubility product Q and compare it to the KSP for cerium hydroxide. So remember, Q you calculate with the same expression that you see for the KSP, only now we don't know whether this thing's at equilibrium, so we just slap in these concentrations, 0.00788 for cerium 3 plus, 1.26 times 10 to the minus 6 for hydroxide. Don't forget to cube that, and we get a Q value of 1.6 times 10 to the minus 20. Well, recall that the KSP for cerium hydroxide is 6 times 10 to the minus 22. So it appears that our calculation of Q gives us a value that's greater than the KSP, and so we conclude, yes, if you adjust the pH to 8.1, cerium hydroxide will precipitate until the solubility product cerium 3 plus times hydroxide concentration cubed decreases back down to 6 times 10 to the minus 22, which is its KSP value. Let's look at a second example related to the first. Suppose we continue to adjust the pH in the solution from this first example, and we actually raised the pH. We raised it to 11.4. Now obviously more cerium hydroxide would most likely precipitate because now we have an even higher concentration of hydroxide. So my question is, what would be the concentration of cerium 3 plus left in solution after cerium hydroxide is finished precipitating at pH 11.4? This is a little more sophisticated question. You might ask, well, why would someone even care about this? Suppose you were tasked with removing cerium 3 plus from a solution because it was bad to have that in solution for some reason. Well, what you're looking to do is drag cerium 3 plus out of solution by forming a hydroxide precipitate. So let's see if adjusting the pH up to 11.4 will get all of the cerium 3 plus out of solution. Well, again, we'll calculate the hydroxide ion concentration at pH 11.4, and we get 2.51 times 10 to the minus 3 molar. Now here's where things would be a little bit different from the first example. What we're going to do is we're going to write the solubility product, but we're going to set it equal to the KSP of cerium hydroxide, and then calculate the cerium 3 plus concentration that's in solution when the hydroxide ion concentration is 2.51 times 10 to the minus 3. That may not make a lot of sense until you just see the calculation. So we'll write the solubility product expression and we'll set it equal to the KSP, and we'll substitute in our hydroxide ion concentration and solve for cerium 3 plus. So I'm solving for cerium 3 plus, so I'd bring hydroxide ion concentration cubed back under the KSP, put in the hydroxide ion concentration, and get a cerium 3 plus concentration of 4 times 10 to the minus 14 molar. What did we just calculate? We calculated the maximum cerium 3 plus ion concentration that can exist in solution in the presence of 2.51 times 10 to the minus 3 molar hydroxide. So this is the cerium 3 plus concentration remaining in solution. All the rest of it's been dragged out and precipitated as cerium hydroxide solid. Now this is a ridiculously small concentration of cerium that remains in solution. And it's so small that we could probably safely say that at pH 11.4, we have completely removed cerium 3 plus from the solution and precipitated it out as cerium hydroxide. Yes, there's a calculated number we can come up with for how much cerium 3 plus is left, but it's so ridiculously small we can say, well, effectively, we've removed it all. Let's do another example. Let's suppose you had two solutions in two separate beakers of two different ionic salts, and you mix those two solutions together in a bigger beaker and stir. And then you ask, what's going to happen? Is anything going to precipitate out? So we have 100 milliliters of a 0.0251 molar solution of barium chloride in one beaker. We have 100 milliliters of 0.0103 molar sodium sulfate in the other beaker. You mix them together. Would you see a precipitate? If so, what would precipitate? Now remember, the total volume when you mix them together is now 200 milliliters, and each solution dilutes the other. We'll see how that plays out. Before we do that and do any calculations, we want to think about what's in solution right after mixing, but before any precipitation, if it's going to occur, any precipitation occurs. So we mix these two solutions together and we freeze time and we look what's present. Well, we have barium ion in solution, we have chloride ion in solution from the barium chloride dissolving. We have sodium ion in solution and sulfate ion in solution from the sodium sulfate dissolving. Now we want to consider what combinations of cations and anions could possibly form precipitates. So let's look at the possible combinations. How about barium with chloride to form barium chloride solid? Well, not likely. Remember, one of the solutions used here was barium chloride and we just diluted it. So barium chloride doesn't seem to have any trouble going in solution at the concentrations that we're dealing with here. How about barium 2 plus interacting with sulfate to form barium sulfate solid? good candidate to precipitate. Why? You find it commonly listed in KSP tables of insoluble salts. So if it's on a table of KSP values and it's anything like this, you know it's not very soluble. So when barium C sulfate, there's a good chance you're going to get barium sulfate precipitate. Now before we make a final judgment, let's look at the other possible combinations. How about sodium ion pairing up with chloride to form sodium chloride precipitate? Not likely. Sodium chloride is very soluble in water, so probably not a good bet here. How about sodium ion pairing up with sulfate to form sodium sulfate? Remember, we'd need 2 of them for each sulfate. Well, not likely. Again, remember, one of the solutions we used in this little experiment was sodium sulfate, and it was all dissolved at that concentration. And when we mixed it with the other, we diluted it, which would keep it in solution all that much better. So I guess our candidate here for forming a precipitate would be barium sulfate. Now, we're not done yet, because just because barium sulfate's a candidate doesn't mean that its Q value is going to come out high enough to precipitate. So let's see what happens here. Let's calculate the concentrations of barium ion and sulfate ion initially right after mixing and before any possible precipitation occurs. Now the number of moles of barium chloride that we added would be the volume of the barium chloride solution times its concentration. So we're dealing with 0.00251 moles of barium chloride. Now out of the barium chloride, we're only interested in the barium ions. And what would be the number of moles of barium ions? Well, since there's 1 barium ion for every barium chloride, you'd have exactly that same number of moles of barium ions contributed by this solution of barium chloride. And to calculate the concentration of barium ion, we would take the number of moles and divide by the total volume, and we get 0.01255 molar. Remember, this is the total volume after mixing. So this is the concentration of barium ion in solution immediately after mixing, but before any precipitation occurs. We can likewise calculate the number of moles of sodium sulfate added by taking the volume of the solution times its concentration and get the number of moles of sodium sulfate. And the number of moles of sulfate would be exactly the same as the number of moles of sodium sulfate, because you get 1 sulfate for every sodium sulfate. And then we can calculate the concentration of the sulfate by taking the number of moles of sulfate and dividing by the total volume, and we get 0.00515 molar. Now our job is simply to calculate a value of Q using the solubility product and the concentrations of barium ion and sulfate ion present in that solution right after mixing. If we put those concentrations in, we get a Q value of 6.46 times 10 to the minus 5. Now that is definitely bigger than the KSP of barium sulfate. So barium sulfate will precipitate after mixing the 2 solutions. So you can see here that the calculations take several steps, but the most important thing to start with was to look at the chemistry of what was going on in the solution immediately after mixing, picking out a candidate for precipitation, and then calculating the concentration of the ions that we have pinpointed after mixing, see if the Q value is greater than the KSP or not. In this case it is, so we'd expect barium sulfate to precipitate after mixing the 2 solutions. In the second part of this lecture, we'll extend some of these concepts to handle a few more complicated, I would say, interesting situations.